Bismillahirrahmanirrahim. Dear students, Assalamu alaikum. Dear students, this video lecture is the continuation of my previous video lecture. In the previous week, we have already learned about the higher order linear differential equations, and we have discussed the three cases: case number 1, case number 2, and case number 3 for the nature of roots of auxiliary equations. So in the first case, we have discussed that when the roots are real and different. In case number 2, when roots are real and equal. Third case, when roots are complex and different. So the fourth case for the nature of roots is when roots are complex and equal. So in this video lecture, I would like to tell you about the nature of roots, case number 3 again, because case number 3 is with the link to the case number 4 for the nature of roots of auxiliary equation. Case number 3 mean when roots are complex and repeated. And case number 4 mean when roots are complex and equal. So you see over here an example when roots are complex and distinct. Suppose m1 is the root, complex root alpha plus iota beta, and m2 is also complex root alpha minus iota beta. These two complex roots are different. So the complementary solution for the auxiliary, for the homogeneous differential equation, higher order differential equation, will be e power alpha x into c1 cos beta x plus c2 sin beta x. Suppose we have a second order homogeneous linear differential equation, y double dash plus y is equal to 0. So this equation can be written as d square plus 1 into y is equal to 0. Now y is equal to 0 is the trivial solution, and we have to find the non-zero solution. D square plus 1 can be written as, for the auxiliary equation, m square plus 1. So m is the root of this auxiliary equation. Now to find the m, we obtain m square is equal to minus 1, which implies that m is equal to plus minus under root 1, plus minus under root minus 1. So under root minus 1 is actually iota. So there is this is a complex number which can be written as 0 plus minus iota 1. So 0 represent alpha and 1 represent beta. By comparison, we obtain alpha is equal to 0 and beta is equal to 1. So the complementary solution for this homogeneous second order homogeneous linear equation, yc is equal to e power alpha x into c1 cos beta x plus c2 sin beta x. And now putting the value of alpha, which is 0, and the value of beta, which is 1, we obtain the complementary solution yc e power 0 into c1 cos x plus c2 sin x, and e power 0 actually 1. So we obtain the complementary solution c1 cos x plus c2 sin x. Now another fourth order linear homogeneous differential equation, y fourth derivative plus 4y is equal to 0, and this equation can be written as d power 4 plus 4 into y is equal to 0. So y is equal to 0 again here is a trivial solution. Now for the non-trivial solution, we have an auxiliary equation m power 4 plus 4 is equal to 0. Now to find the roots m for this auxiliary equations, dividing both sides by adding and subtracting 4m square. M power 4 plus 4m square minus 4m square is equal to 0. Now m power 4 plus 4m square give formula a plus b whole square. So m square plus 2 whole square. This formula m square plus 2 whole square give again m power 4 plus 4m square, a square plus b square plus 2ab. Now minus 4m square mean 2m whole square. Now again we obtain a formula a square minus b square, which can be written as a plus b into a minus b. So m square plus 2 plus 2m, m square plus 2 minus 2m. So these are two quadratic equations. So first of all, find the first quadratic equation, m square plus 2m plus 2. To solve this quadratic equation by using the quadratic formula, we obtained the coefficients a is equal to 1, b is equal to 2, and c is equal to 2. Now solve this quadratic equation by using the quadratic formula, m is equal to minus b plus minus under root b square minus 4ac divided by 2a. So m is equal to minus 2 plus minus 4 minus 8 under root divided by 2. Putting the value of a, the value of b, and the value of ac in this discriminant part, we obtain m is equal to minus 2 plus minus under root minus 4 divided by 2. Under root minus 4 actually equal to 2 iota. Now taking common from this expression, taking common 2, we obtain minus 1 plus minus iota. So this is actually represent the alpha value, and this is represent the beta value. So the first quadratic equation gave one complex root. Now the second quadratic equation, to solve this second quadratic equation, we obtain here the coefficient a is equal to 1, b is equal to minus 2, and c is equal to 2. To solve this quadratic equation again by quadratic formula, we obtain here minus b, but in the equation b contain the coefficient minus 2, so minus minus plus 2, and plus minus b square means minus 2 square 4 minus 4a and c, so 2 to the 4 and 4 to the 8. So this implies that m is equal to 2 plus minus under root minus 4 divided by 2. Under root minus 4 again equal to 2 iota, and now taking common 2 from this expressions, we obtain 1 plus minus iota. So in this this quadratic equation gave another complex root. So these are two complex different root. So this is actually called the case number 3. Roots are complex but different. 1 plus minus iota beta. So there are two complex root, different complex root. So the first complex root obtain alpha 1 plus iota beta 1, which is equal to this minus 1 plus minus iota 1. So 1 is beta 1 and minus 1 is alpha 1. Alpha 1 is equal to minus 1 and beta 1 is equal to 1. And the other complex root 1 plus minus iota, you see over here, this is alpha 2 and now 1 is beta 2. So the complementary solution, there are two complementary solutions. So add these two complementary solution, we obtain the whole complementary solution for the given homogeneous fourth order linear differential equation. Since the given equation fourth order differential equation, so there will be four constant c1, c2, and similarly c3 and c4. This represent e power alpha 1 x into c1 cos beta 1 x plus c2 sin beta 1 x. This represent the first complementary solution due to the first quadratic equation, and plus this is the another complementary solution due to the second complementary solution, because we have two complex different root. Now e power alpha 2 into c1 cos beta 2 plus c2 sin beta 2 x. Putting the value of alpha 1 beta 1 and alpha 2 beta 2, we obtain the is a whole complementary solution e power alpha x into c1 cos beta x plus c2 sin beta x, but beta 1 is equal to 1 1, and so this is the e power minus x into c3 cos beta x plus c4 sin beta x. First we put alpha minus 1 in beta 1, and then we put alpha 1 beta 2 also 1. So this is the whole complementary solution. Now the new case, roots are complex and repeated for this lecture. Now we discuss the case when auxiliary equations m of m is equal to 0 has repeated complex root. Suppose it had two pair of complex and repeated roots, alpha plus minus iota beta, alpha plus minus iota beta. These two complex roots are not different. These two complex roots are equal. Then suppose since these two roots are repeated are equal, so this is actually called, suppose m1 alpha plus iota beta. Then the complementary solution and another root, suppose m2 alpha minus iota beta, be repeated twice. Then the complete solution, complementary complete solution, e power alpha x into c1 plus c2 x into cos beta x plus c4 in plus c5 x into sin beta x. Now suppose you see over here this is an example, d power 4 plus 8d square plus 16 into y is equal to 0. The auxiliary equation for this fourth order linear homogeneous differential equation is m power 4 plus 8m square plus 16 is equal to 0, and this is actually equal to the m power 4 m square plus 4 whole square. If we expand this formula again, we will obtain m power 4 plus 8m square plus 16 is equal to 0, because a square m square whole square mean m power 4, b square 8 square 4 square mean 16, and 2ab, this is actually a and this is actually b, 2 for the 8, we obtain 8m square. Now whole square, m square plus 4 whole square mean we can write m square plus 4 into m square plus 4. So m square plus 4 equal to 0 implies that m square is equal to minus 4, and taking square root on both sides we obtain m is equal to plus minus 2 iota. And again we can write m square plus 4 is equal to 0. We will obtain another roots to plus minus 2 iota. So the roots are complex but repeated. So the complementary solution will be in this form. Now you see over here, this is the complementary solution, e power alpha x into c1 plus c2 x into cos beta x plus c4 plus c5 x into sin beta x. Now putting the values alpha 0 and beta 2, we obtain the complementary solution e power 0 into c1 plus c2x into cos beta 2x plus c4 plus c5x into sin 2x. So the complementary solution now can be written as c1 plus c2x, actually e power 0 is equal to 1. So we obtain c1 plus c2x into cos 2x plus c4 plus c5x into sin 2x. Now another example, y triple dash minus 2y double dash minus 4y dash plus 8y is equal to 0. So this equation can be written as d cube minus 2d square minus 4d plus 8 into y. So y is equal to 0 will be the trivial solution. Now the non-trivial solution, for the non-trivial solution we consider the auxiliary equation m cube minus 2m square minus 4m plus 8 is equal to 0. So by factorization, taking m square from these two terms, m square into m minus 2, and taking common minus 4 from these two terms, we write m4 into m minus 2 is equal to 0. So m minus 2 again common, we can write m square minus 4 into m minus 2, and m square minus 4 obtain a formula a square minus b square, which can be written as m square minus 2 square, and can be written as a plus b into a minus b, mean m plus 2 into m minus 2, and this m minus 2 as it is. Now dear students, in this question you see over here, actually the roots are m1 and m2 roots are real and repeated, but in this case roots are real and different. m3 is the different root. So this is actually case number 1 and case number 2 combined. This is actually the case number 1 and this is the case number 2. So for the practice, you see over here, this is an example when roots are real and different, and when roots are real and repeated. So case number 1 and case number 2 appear in this problem for the nature of roots of the auxiliary equation. So the complementary solution is c1 plus c2x n2 e power m1. This is actually m1 plus c3 e power m2x. Minus 2 is the m2. Now another problem you see over here, y fourth derivative minus 2y triple dash plus 2y double dash minus 2y dash plus y is equal to 0. This fourth order linear homogeneous differential equation can be written as d4 minus 2d cube plus 2d square minus 2d plus 1 into y is equal to 0. So y is equal to 0 will be the trivial solution, and for the non-trivial solution we obtain auxiliary equation m power 4 minus 2m cube plus 2m square minus 2m plus 1 is equal to 0. So putting m is equal to 1. To find the roots of this equation, first of all suggest a root which satisfied this equation. When a root satisfied this equation, then that will be the exact root for this polynomial. Now m is equal to, suppose m is equal to 1, putting in this equation 1 minus 2 plus 2 minus 2 plus 1, and this is actually equal to 0. plus 1 and plus 1, plus 2, plus 2 minus 2 cancel, plus 2 minus 2 cancel. So we obtain this left hand side equal to 0 and this side is also equal to 0. So m is equal to 1 is the root. Now we have to find the other 3 roots. M power 4 mean we should to find 4th root for this auxiliary equation. So by using synthetic division, this is actually the first root. Now 1 is it is multiplying 1 into this one, we obtain 1. Now adding these two terms, we obtain minus 1. Multiplying minus 1 to this one, we obtain minus 1. And now adding these two terms, we obtain 1. Now multiplied this one to this one, we obtain 1. Minus 2 plus 1 is equal to minus 1. Now multiplying this minus 1 to this one, we obtain minus 1. And minus 1 plus 1 is equal to 0. So the remainder is 0. Now the depressed equation will be equal to m cube minus 2m square, m cube minus m square plus m minus 1 is equal to 0. And you see over here, this is the depressed equation, m cube minus m square plus m minus 1. Now again putting m is equal to 1, this equation is satisfied. For m is equal to 1, m 1 minus 1 plus 1 minus 1 is equal to 0, and this implies that left hand side also equal to 0 and right hand side also equal to 0. Now again by synthetic division we can find the other roots, but synthetic division mean equation will be depressed. When equation depress from the higher degree to the lowest degree, then we can easily solve the equations by any quadratic formula or by taking common. But with the highest degree, solution of equation is difficult. So synthetic division help us. Actually synthetic division depress the degree of the auxiliary equation, and when the degree of the auxiliary equation decrease, then the solution will be easy. For the auxiliary equation we can easily find the roots of the depressed equation. So again here I would like to depress the degree of this equation, and if we take common m square from this equation, then we can find m square into m minus 1, and taking common plus 1 we obtain m minus 1. So by taking common m square from this term and 1 from this term, we can solve this polynomial by taking common. But if we use synthetic division, we can easily use again the synthetic division. So since m is equal to 1 again is the root of this depressed equation, so first of all put the coefficients. This is the coefficient of m cube, this is the coefficient of m square, this is the coefficient of m, and this is the constant. So put here the roots. Now 1 is it is multiplied 1 to 1, we obtain 1. Adding these two terms, 0. Multiplying 1 to 0, this is 0. Now adding these two, 1. Now 1 multiplied 1 we obtain 1. Minus 1 plus 1 is equal to 0. The remainder is 0. So the depressed equation, this is actually now the coefficient of m square, and this is the coefficient of m, but the coefficient of m is 0. So we can write again the constant coefficient, the constant value. This is the coefficient of m square, and this is the constant. M square plus 1 is equal to 0, and now m square is equal to minus 1. This implies that m is equal to plus minus under root minus 1, and under root minus 1 is actually equal to iota. So in this example we obtain two real roots, 1 and 1. Roots are real and repeated, and 1 is the complex root. So you see over here, dear students, note that this point is very important. This is actually alpha 0 plus minus iota this is equal to alpha, and the coefficient of iota is 1, so beta is 1, and the other two roots are real and repeated. So we can write one solution for case number 3. Roots are complex and different, and other two roots are real and repeated. So case number 2 and case number 3 are now combined for the complementary solution of the given 4th order linear homogeneous differential equation. Actually these are two roots, 0 plus minus iota. So there are two roots in this expressions, in these there are also two real roots and two complex roots, 0 plus iota and 0 minus iota. For these two complex different root, we can write the complementary solution e power alpha x into c3 cos beta x plus c4 sin beta x. So fourth roots are appear for the given fourth order linear homogeneous differential equation. Two roots, complex two roots but different, and two real and equal roots. So the complementary solution c1 plus c2 x into e power mx plus e power alpha x into c3 cos beta x plus c4 sin beta x. Now putting the value of m is equal to 1, which is real and equal. So c1 plus c2 x into e power 1x plus e power alpha value is 0 into c3 cos beta value is 1 plus c4 sin x. Now e power 0 is actually equal to 1. So c1 plus c2 x into e power x plus c3 cos x plus c4 sin x. This is the solution of the given fourth order linear homogeneous equation. Now this is the fifth order linear homogeneous equation. Y fifth derivative minus 16 y dash is equal to 0, which can be written as d power 5 minus d into y is equal to 0. Taking y is equal to 0 will be the trivial solution for the given fifth order homogeneous linear differential equation. Now to find the non-trivial solution, the non-zero solution for this homogeneous linear differential equation, we obtain auxiliary equation m power 5 minus m is equal to 0. Taking m common from this polynomial, we obtain m into m power 4 minus 1 is equal to 0, and this implies that m power 4 minus 1 mean m square minus 1 into m square plus 1. This is actually a square minus b square formula. So now this is again formula a square minus b square. So m square minus 1 can be written as m plus 1 into m minus 1, and m square plus 1 is it is. So dear students, note that we have three real roots and different. M is equal to 0, m is equal to minus 1, and m is equal to plus 1. And from this expression, we will obtain the complex root. You see over here, m is equal to 0, m is equal to 1, and m is equal to minus 1. So these three roots are real and repeated, and m square plus 1 is equal to 0 implies that m square is equal to minus 1. Taking square root, we obtain m is equal to plus minus under root minus 1, which implies that m is equal to plus minus iota. So there are three different real roots and two complex different roots. 0 plus iota is first complex root, 0 minus iota and the second complex root. For the complex root, you see over here, this is the complementary solution for the complex number, and this is the complementary solution for the real and unequal roots. So roots are real and unequal, this is case number 1, and roots are complex and unequal, this is case number 3. So putting the value of m1 value is 0, m2 value is 1, and m3 value is minus 1. You see over here, this is m1, this is m2, and this is m3. And for the complex root, the complementary solution e power alpha x into c4 cos beta x plus c5 sin beta x. So putting the value of alpha value is 0, e power 0, and e power 0 actually equal to 1. So is a whole complementary solution for the given fifth order homogeneous linear differential equation as c1 plus c2x plus c3 e power minus 1x plus c4 cos x plus c5 sin x. Now dear students, in this slide actually all the cases of the roots for the auxiliary equation discussed. So dear student, first of all, write the auxiliary equation for the higher order linear homogeneous differential equation, and then find the roots for the auxiliary equation. The complementary solution depend on the nature of the roots of the auxiliary equations. So note that there are 4 cases for the nature of the roots of the auxiliary equation. So definitely there will be 4 different formula for the complementary solution. So for each case of the roots of the equation, note the complementary solution for the auxiliary for the given for the given higher order homogeneous differential equation. You see over here, I would like to tell you again, when the roots are real and unequal, then the complementary solution will be in this form. But when the roots are real and repeated, then the complementary solution will be in this form. You see over here, this part actually represents the roots are real and repeated. And when the roots are complex and unequal, then solution will be in this form. And when the roots are complex and repeated, you see over here, the solution will be in this form. And now this is the end of this segment. Thank you. Allah Hafiz.